Hi everyone. How do you graph odd degree polynomial functions? What do they look like in the long run? In the long run, they look like snakes. Now, if you look at the graph of y equals x cubed, or for that matter, y equals x, there are no turning points, so you don't have to have any turning points. But if you do turn around, you better turn around again. So anytime you turn around, there better be a partner turnaround point. If you turn around again, you better turn around again. These have to come in pairs. So here you could have 0 turning points, 2 turning points, 4 turning points, and so forth. The graph of an odd degree polynomial must have an even number of turning points. Notice the parities here are different. A parity means odd versus even. Oh, by the way, regarding odd degree polynomial graphs, they always have to have a real zero. Why is that? Why do odd degree polynomial functions always have to have a real zero? Because the graphs always have to have a what in the xy plane? A snake always has to have an x-intercept. An odd degree polynomial must have at least one real zero because the graph must have at least one x-intercept. Good to know. So now, there's a handy-dandy algorithm for figuring out how many turning points you can have. Because here's what you do. To find the possible number of turning points for a non-constant polynomial graph, here's what you do. Polynomial graph of degree n. Here's what you do. You start with, now this is to get a list of the possible number of turning points. You start with n minus 1. That's going to be the possible number, the maximum possible number of turning points. Then keep counting down by 2s and stop before you hit negative numbers, because you cannot have a negative number of turning points. So for example, let's say you have a third degree polynomial, n equals 3. Well, you start with n minus 1, which is 2. Count down by 2. 2 minus 2 is 0. So you can have 2 turning points or no turning points. And of course, you cannot have negative 2 turning points. So you stop at 0. And that makes sense, right? We saw that. The blue graph had 2 turning points. The red graph had no turning points. These were both cubics, third degree. Why does this work? Well, 3 is an odd degree. And remember, for an odd degree polynomial, you have to have an even number of turning points. Well, if n is odd, n minus 1 is guaranteed to be even. These are all guaranteed to be even. And remember our rule from up above. Remember that for a non-constant nth degree polynomial, you can have no more than n minus 1 turning points. N minus 1 is the maximum possible. So when you list out the possible numbers of turning points, you start with n minus 1, the degree minus 1, and you count down by 2s. And of course, you cannot have a negative number of turning points. Now, what about a 6th degree polynomial graph? How many turning points can a 6th degree polynomial graph have? Again, let's use the algorithm. We begin with n equals 6. That's the degree, and it's even. So we start with, to get our list of the possible numbers of turning points, we start with n minus 1, which is 6 minus 1, or 5. Notice that 5 is odd. Remember, an even degree polynomial graph has to have an odd number of turning points so that it goes back to where it comes from. Here we have 5 turning points. 1, 2, 3, 4, 5. There's some 6-degree graphs that do this. 5 is the maximum possible, and it's odd, so that's legal, and then you keep counting down. So we have 5, we start with 5, count down by 2's. 5 minus 2 is 3, 3 minus 2 is 1. And we cannot go to -1. We cannot have a negative number of turning points. So a 6-degree polynomial graph could have 5 or 3 or 1 turning points. It's got to turn around at least once, otherwise it can't be a bull. So 5, 3, or 1. Remember, only high-degree polynomial graphs can be very wavy. Here you have 1 turning point, here you have 3. And there are others with 5. Okay, so again, start with n minus 1, the degree minus 1, count down by 2's. Stop before you reach negative numbers. That's to get the list of possible numbers of turning points. As for which case you actually have, well, take calculus. And what are you going to look for in calculus? You're going to set the derivative equal to a certain number and solve for x. What is the slope of a horizontal tangent line? Notice at these turning points, these relative max and min points, you have horizontal tangent lines. The slope of the tangent line is the derivative. You want to set the derivative equal to, what's the slope of a horizontal line? 0. Set the derivative equal to 0, solve for x. And that's going to help locate these turning points. That'll be for calculus. Okay. Next up, we're going to talk about x-intercepts.